Now, early statisticians had a particular form, they had developed a particular form in which they could express this splitting up of the sum of squares, which they called analysis of variance. So, in order to understand that, let's take our example, which is like this: that we have got the box diagram where I have got 3 different inputs. I'll assume that all of them are factor inputs, following the concept, following the examples that generally early statisticians used to take. And this is the particular diagram where I assume that we have the necessary orthogonality relationship. Then they would like to express this situation using a table. In this table, they will show all these different directions, all the different orthogonal directions. So they have basically split up the total Rn into various mutually orthogonal subspaces. One subspace devoted to the intercept, another subspace devoted to the red input, etc., etc., and the final subspace devoted to the orthogonal complement of column space of X. So they will devote one row of this table to each of these things, and they will also ascribe the different rows to the different sources. So by source we mean the first one is intercept, the second one I have called red, whatever that factor is. So if that is variety, then I call it variety. If the next thing is gender, it is gender. If the third thing is smoking habit, it is smoking habit. And the last thing is always error. Error means the component which is orthogonal to column space of X. And then at the end you write down the total. Total is basically the squared norm of the entire Y vector. This column will be followed by the degrees of freedom column, which is just a fancy term for the dimensions of the different subspaces. So the intercept thing will always have degree of freedom 1, and the total thing will have degree of freedom n, because we are working with Rn, and the different things will have corresponding degrees of freedom. Now, people usually did not like to put that intercept thing separately. Even in case of that one factor input, we really did not have 3 terms. So the way I have written, it seems that there should be 3 terms. One because of the intercept, one because of that factor input, one because of error. But you remember when you wrote down that particular sum, that algebraic identity, we had only 2 things, within sum of square and between sum of square. So this intercept term, people naturally wanted to hide, because the intercept really does not correspond to any of the inputs. All the other things correspond to some arrow or other, but the intercept thing is not corresponding to any arrow. So people had a tendency to hide that. So basically they will subtract that from the total, and the new total will be called adjusted total, and the degrees of freedom has gone down n-1, and you do not have the first row. So that is the more traditional way of expressing any such thing. Now also the sum of square, because of error, that is what initial statisticians call the within sum of square, that is now called the residual sum of square. Whatever we have called the residual sum of square is this. It is the norm square of this part, this black arrow. So you have got this kind of a table. Now once you have this table, we can add more things. And just remember one point, that is the various entries that we are adding here, these are nothing but the norm square of the different components. So the norm square of the different components. So here I will have the norm square of the total thing, that is norm square of y, summation yi square, subtracted from it the norm square of the gray arrow. That will be the adjusted sum of square, which you can easily check will be n times y bar squared. And similarly you will have the squared length of the red arrow here, squared length of the purple arrow here, squared length of the blue arrow here, because of Pythagoras, and the orthogonality condition that we have assumed, they will all add up. Now, the next thing that they would typically compute will be the mean squares, so the MS. So these are nothing but sum of square divided by the degrees of freedom, that's the derived column. And this is because they are trying to move towards the F statistic. So all the MSs are computed as sum of square by the corresponding degrees of freedom. In particular, the quantity that you will get here, that will be our familiar unbiased estimator of sigma square. Then they will compute the F statistic, which is nothing but dividing all these mean squares by this estimate of sigma square, and then you will get this F statistic, this F statistic, this F statistic. This F statistic will test whether the red arrow has any input or not, has any influence on the output or not. So if this is insignificant, small, in that case you will say that the red input has got no effect. Similarly, if this number is small, then you will say that the purple input has got no effect. If this is small, then the blue input does not have any effect. Obviously, you do not have any entry here corresponding to the error row, because the error mean square is what you are using as your yardstick. That is your acceptable level of error, and you are comparing all other sum of squares in terms of that. So if this length is acceptable, compared to that, do you think that the red length is of any importance or not? So you are dividing squared length of this by squared length of this after appropriately scaling by the degrees of freedom in order to get your F statistic. So that is the basic idea. And this table came to be known as the ANOVA table, analysis of variance table, and for a long time this ANOVA table was considered to be the most important output of a linear model analysis, and it was motivated completely from the viewpoint of the setup where we have only factor inputs.